Differential and integral operations 3. Now we're doing the third part. Our vector is v0x over square root x squared plus y squared ex hat plus v0y over square root x squared plus y squared ey hat. We're performing the line integral on this closed path, closed contour, dr cross v. And remember that on 1 and 3, dr is dy ey hat, and on 2 and 4, it is dx ex hat. So I have to pay attention to what is fixed on each of these contours. Okay, so for part C, we're dealing with our new vector v, which is v0 x divided by square root x squared plus y squared ex hat plus v0 y divided by square root x squared plus y squared ey hat. All right. Now, along the segments 1 and 3, let's recall our dr vector. Dr on segment 1 is equal to dr on segment 3, which is dy ey hat, and dr differential displacement on segment 2 is dr on segment 4 equal to dx ex hat. And therefore, for dr1 cross with vector v, we will have dr3 cross with vector v. They're the same thing. It is now we can check here, because we have ey hat here, so there's no contribution from ey hat cross ey hat, but ey hat cross ex hat will give us minus ez hat, as we have seen in this cyclic permutations. Ey hat cross ex hat gives us minus ez hat. All right, so this will give me x v0 divided by square root x squared plus y squared dy in minus ez hat direction. And for this segment 2 and segment 4, dr cross v is going to be now, because ex hat cross ex hat will give us 0, ex hat cross ey hat will give us ez hat. So this will be y v0 divided by square root x squared plus y squared. And we have dx in plus ez hat direction. So let's double check here. We have dr cross v, ey hat cross with ex hat, which gives us minus ez hat, and we have x dy. And here for these two segments, we have dx ex hat cross ex hat is 0, but we will have y dx ex hat cross ey hat giving us ez hat. So when I write the closed path integral dr cross with v, this will be the closed path integral from 1 to minus 1. So on segment 1, we go from on segment 1, we actually go from minus 1 to plus 1 on the y-axis. So this is going to be integral from minus 1 to plus 1. And here x is fixed at 1, so we will have v0 divided by square root 1 plus y square dy, and this will be in a minus EZ hat direction. But we can get rid of the minus EZ hat, make it plus EZ hat, and change the order of the integration from plus 1 to minus 1. So that takes care of the minus sign. And then we have plus the integral over the third segment from 1 to minus 1. On the third segment, y is equal to, x is equal to minus 1, so we have minus v0 dy divided by square root 1 plus y square, x square is 1, and this is in minus EZ hat direction. Now you can see I have two minuses, they cancel out, so this becomes plus EZ hat. And then I have for the segment 2, on segment 2 we have minus 1 to plus 1. So this was segment 1, this was segment 3. Now I'm doing segment 2. On segment 2, x goes from, let's double check, x goes from plus 1 to minus 1. So this integral is plus 1 to minus 1. And here we have a y v0 dx EZ hat. But what is the value of y on the second segment? Y is equal to plus 1. So here we substitute 1. So this will give us v0 dx divided by square root 1 plus x square. And that's in EZ hat direction also. And as for the fourth segment, on the fourth segment, we go from minus 1 to plus 1, and y is equal to minus 1 on the fourth segment. There, y is equal to minus 1. We go from minus 1 to plus 1. So this will give us minus v0 dx EZ hat divided by square root 1 plus x square. And again, I can get rid of this minus sign by changing the order of the integration to be from 1 to minus 1. Now you can see that I have obtained exactly the same thing for all four segments. Therefore, what I really have at the end is 4 times the integral from plus 1 to minus 1 v0 dx divided by 1 plus x square root in EZ hat direction. Now notice that here I had dy and y is changing from plus 1 to minus 1. Here I had dx, y is changing, x is changing from plus 1 to minus 1, but it doesn't matter, so I can replace x with y with x. It's a dummy variable here, so I obtain exactly the same integrals. Now the question is, how do I perform this integral? So let's say that x is equal to tangent theta. So we have to make a transformation to theta, so that dx is equal to secant square theta d theta, the derivative of the tangent. Now if I draw a right triangle here, this is one of the well-known tricks in performing integration. I will have, for this angle being theta, tangent theta is x. So Pythagorean theorem tells me that the hypotenuse should be square root of 1 plus x squared. And what is cosine theta? I can read that cosine theta is 1 over square root 1 plus x squared. Okay, now x is going from plus 1 to minus 1. When x is equal to plus 1, theta is equal to pi over 4. When x is equal to minus 1, theta is equal to minus pi over 4. All right. So I will have tangent pi over 4 equals 1 and tangent of minus pi over 4 is equal to minus 1. So I can see that this integral can be written as 4v0. Now theta goes from pi over 4 to minus pi over 4. Cosine theta secant square theta d theta. So I've substituted for 1 over square root 1 plus x squared cosine theta. And cosine theta gets rid of one of the secants because secant is 1 over cosine. So this turns into 4v0 integral from plus pi over 4 to minus pi over 4 secant theta d theta. The integral of secant is a natural logarithm absolute value of secant plus tangent. This will be evaluated between plus pi over 4 and minus pi over 4. And when we do that, we obtain 4v0 natural logarithm square root 2 minus 1 minus 4v0 natural logarithm square root 2 plus 1. And this is all in easy hat direction. So let's not forget that. This is an easy hat direction. And final answer, then if you numerically evaluate this, the closed path integral dr cross v is minus 7.05 v0 easy hat. So for this part of the problem, we have a different vector, x over square root x squared plus y squared in ex hat and y over square root x squared plus y squared ey hat multiplied with v0. Noting that the r vectors on segments 1 and 3 and 2 and 4 were identical, so I have rewritten the r cross v's and then realized that what I obtain for each of these segments is the same integral. Integral from 1 to minus 1 v0 dx over square root 1 plus x squared easy hat. 4 times of this integral. So to perform this integral, we have a transformation, x equals tangent theta transformation. And we find that when x is equal to 1, tangent, the theta is pi over 4. So sine pi over 4 over cosine pi over 4 is 1. When x is equal to minus 1, we have a sine of minus pi over 4, which is minus sine of pi over 4, divided by cosine of minus pi over 4, which is cosine pi over 4, giving us minus 1. So these are the limits of the new and limits of the integration. For 1 over square root 1 plus x squared, we substitute cosine theta. Cosine theta, square root of 1 plus tangent squared theta, that's going to give us when we substitute here x equals tangent theta 1 minus 1 plus tangent squared theta square root, which is going to give us secant square. So that's going to give us basically, for dx, we have secant squared theta d theta. For 1 over square root 1 plus x squared, we have cosine theta. So that's what I have here. Cosine theta gets rid of one of the secants. And here I'm left with integral of secant theta d theta, which is natural logarithm of absolute value of secant plus tangent theta. Evaluating between plus pi over 4 and minus pi over 4, we have our numerical answer minus 7.05 B0 EZ hat.